believe this was, yes, yeah, this was the title. I just forgot what was the title. What was the title? So this is joint work with Padraig Condon and Alberto Espuny Diaz and me and Osthus. So just like many of the extremal graph talk, let's start with the Dirac theorem. So what was the Dirac theorem? So if you have a n vertex graph, and if we know that the minimum degree of n vertex graph C is at least n over 2, and G is Hamiltonian. So it tells you that if you have a graph and whose density condition is, whose density is above something. So here the density is measured by the minimum degree. So if graph is dense enough, then we can find some structure there. In this case, this is a Hamilton cycle, which is a cycle passed through all the vertices. And this is actually tight by considering, complete bipartite graph, which is slightly unbalanced. And this doesn't contain any Hamilton cycle, and it almost satisfies this density condition. But this example is very special. This is very not typical example. Meaning that if you just consider all the graphs with the density slightly below, then most of them doesn't look like this. So we can, that is true. Of course. Yeah. So we can ask so this is the worst case. So if we are slightly below this density, then there exists some worst case scenario that we are failed to find the structure that we wanted. Then we can ask that what if we just, don't think about the worst case, but we just consider the typical scenario. Then, that can be, made rigorous by considering the random graph. So we can ask that, if you consider the graph with certain density, and then among all those, graphs with a certain density, can we say that most of them, have the Hamilton cycle? Can we find the density which satisfies the thing that I just said? So, for example, we can, ask that it says Hamilton cycle. So this random graph model has a Hamilton cycle with high probability is exactly what I just said. With this density, if you consider the older graph with approximately this density, and most of them satisfy, this property of having Hamilton cycle is exactly this for P at least something. So we can ask this. And this was, answered by several people. Initially, Eridich and Lenin considered a similar question for perfect matching instead of Hamilton cycle. Say we want to find the perfect matching, and they show that C log n over n is enough. That was Eridich and Lenin in 60s. And later, Pósa and Kolchunov show that the Hamilton cycle also can be found with the same, density bound. And later, Komrosh and Semoredy in 83 determined the precise threshold. So say, if, let's write little, omega of 1. If we have a P is at least log n plus log n plus omega 1. So this is some function which goes to infinity. And over n, then this has a Hamilton cycle. And this is, sharp in the sense that if we subtract this, positive function, then almost surely, with high probability, it doesn't have a Hamilton cycle. So, this is more or less tight. And in
omega 1 on top of 1 over n,
And also there are, so this kind of answers that, answers the previous question about the typical graphs. At which density, typical graphs has a Hamilton cycle. And also there are more precise results than this, which is called heating time result. So instead of considering this GMP is that you have n vertices, then each pair you flip a coin to decide whether to add an edge or not. You can consider the similar, model. There are n vertices, and there are n choose 2 pairs. You choose one of them uniformly at random and add. And then there are n choose 2 minus 1 remaining unmatched pair. And then you also choose one of them and then add. You repeat it until you have some number of edges, or you stop it when you want. Then, what's known is that Borlovazzi and Thomason shows that in this model, you will have a perfect matching as soon as you have the minimum degree 1. So you keep do this. Of course, with high probability. You keep do this, and at certain moment, there will be, so at first, most of them are isolated vertices. But while doing that, the number of isolated vertices go down by 1 and 1 and 1. There are exactly some moment, exact number of edges where you remove the last isolated vertices. They show that at that moment, you can find the perfect matching with high probability. And Aitai, Komroshi, and Sam already in 85 show that you can find the Hamilton cycle at exact moment that the minimum degree becomes 2. So which is in some sense more precise than this GMP.
How many edges do you need to add on average until the average?
This times n choose 2. So it's roughly log n times n over 2.
So others are.
More or less equivalent. You have to define what equivalent means, but yeah. So let's define some concept like resilience. So in the title we have this what's the title? Resilience version or resilience 2 version?
Resilience.
Yeah, okay. Anyway. In order to talk about resilient version of something, we need to know what resilience is. So precisely, it's called local resilience, but we are not going to consider global resilience in this talk. Just so whenever I say, then this is local resilience. So if you have a graph G, then we say the local resilience of this graph G with respect to some graph property P. So this is property. Always I have a trouble writing some, calligraphic error, but this is the maximum R such that for any subgraph H of G with maximum degree strictly smaller than R, G minus H satisfies T. So you can consider in this way. So you have a graph G, and our goal is to, make sure that this graph satisfies certain property P. In our case, we want to find the Hamilton cycle in the given graph. But there is some bad guy or enemy or adversary who doesn't like me. Somehow he wants to screw our purpose. I don't know the reason, but what he does is he deletes some edges. But there are some limits that he can delete. He cannot delete too many edges at each vertex. I mean, if there is no limit, then it's too not fair, right? I mean, at least we have to have something. So, so the enemy can delete the edges so that the damage is not too much. And we want to measure the damage that we can endure. That's the local resilience of this graph G. And with this concept, we can restate this Deryk theorem. So what Deryk theorem says is that if you consider complete graph on n vertices, and this has resilience n over 2 with a floor with respect to having Hamilton cycle. Let's just write M. You're from Germany. anyway. Yeah. Germany is famous for Hamilton cycle. Yeah. Anyway, where was I? Yeah. You can check this floor sign is correct. I was having trouble with like plus minus 1 because this has degree n minus 1 and Deryk theorem has n over 2. But anyway, so we can restate this Deryk theorem in this way. Then whenever we have a certain, property in deterministic graph or in a complete graph, it's natural to ask what happens on random graph. Because this complete graph is nothing but a random graph with a probability 1. For other p, so our question is that, one natural question is that what's its resilience? Something with respect to Hamilton cycle or here is something. In fact, maybe I should have kept it. Anyway, I already have deleted. So, Sudakov and Vu first show the resilience for having perfect matching. So GNP has local resilience. Let's just write resilience for every. Just forget the. Omit the local for now. So this is with respect to having perfect matching. If K is LHC times log n over n. So it's like similar as a complete graph. Graph with minimum degree n over 2 has a perfect matching. So it's a generalization of that. And Lee and Sudakov, so this was 0A and 12, show that similar thing for the Hamilton cycle. So here, this number is natural because if you consider the GMP and all the vertices have a degree more or less 1 plus minus 0.1 times NP. This is half and slightly less. Because we are considering the random graph, we don't know what exactly happens. So there are some rooms that need to be there. So this is some small epsilon. And recently, there are even more precise results. conformally and independently. This way. Yeah. 내놔도 Tger Deryk, and I think both of them are 19. They show that for the heating time, version, we can also prove, resilient result for the heating time version. So basically, you consider the heating time model. So you add the H one by one, and as soon as you have a minimum degree 2, the graph is resilient in the sense that T minus H has Hamilton cycle for if this holds for all B. So you can delete the edges, but in this case you have minimum degree 2, so there are vertex with exactly degree 2. Here, if this is 2, then this number is strictly smaller than 1, so you are not allowed to delete any edge. But if this is 3, then you can delete 1. So with that, they show that exactly that moment, the graph is resilient. And also there are other resilient results. So for example, maybe I wouldn't just write it and then I just say. So you can consider like pancyclicity. So here you just consider Hamilton cycle, but you can consider when the graph becomes pancyclicity after this deleting some edges. So Krivlevich, Lee, Sudakov consider the pancyclicity, and Storyk, Tger, Deryk consider the case power of the cycles of all lengths, and also almost spanning bounded degree trees were considered by Barlog, Saba, Semoti, and triangle factors is considered by Barlog, Lee, Samosty, and bounded degree graph, which is almost spanning, or spanning even, was considered by Allen, Bocher, Ehrem, Mueller, Terras, and Huang, Lee, Sudakov. So there are other things that, besides the Hamilton cycle or perfect matching, people have considered many other things, in the view of the resilience. So what we want to do is, instead of Dirac theorem, we can consider Pósa theorem. So Pósa theorem is a bit stronger than Dirac. So if you have a graph G with n vertices, and then if we have the degree sequence d1 to dn, degree sequence of that graph, and if di is at least I plus 1 for all I at most half, then this is Hamiltonian. She has a Hamilton cycle. So basically, if you just consider the Dirac theorem, then d1 to dn, if your degree is above this, then you are Hamiltonian. But the Pósa theorem is that if your degree is lies above this kind of. Do you have a problem, or is it? Okay, okay. Then I mean it's a Hamiltonian. And also there are more general Padraig theorem, which says that again T1 to Tn, and if either Di is bigger than or equal to I plus 1, or Tn minus I, was it n minus I? Yeah. It's at least n minus I for all discrete mode. Then she has Hamilton cycle. So in this Pósa's version, you can consider that you have a Kn and you delete H, and that is G. So again, H is the damage that adversary is doing. And if the damage is under this, then it is Hamiltonian. So you can kind of flip the degrees in H, and it looks this way. That's the maximum damage that you can do. So what's our theorem? So we prove that we can generalize Pósa theorem. Okay, maybe we make it precise. For epsilon positive, there is a C. So if you consider the random graph, G and T, it satisfies the following. And let's give some name to this following, Pósa resilience. If we have a subgraph which has an ordering of the vertices we want to be n, with its degree are decreasing, because here the degrees are increasing, that means h degree is decreasing. And if the degree of Bi in H is almost n minus I P minus epsilon n P, for all I almost n half, then G minus H is Hamiltonian. So this was for all H, then we say that this G is Pósa resilient, and we said that the GMP satisfies this. So you see that we subtract this epsilon and P to give a bit more room, just like you have a little one term here. And then natural question is that, okay, this is Pósa resilient. Then what should be the Padraig resilient? The natural thing is that you write down same thing, because I don't want to write down same thing, so I just write 11 everywhere. And either you have this, or other one, th p n minus I. So this is natural. Maybe blue color was not a good choice. Maybe on the screen it's not so visible. Anyway, so this is the natural guess of fatal resilience. Right? Pretty natural. I mean, so you have this, so you write this, and this is subtracted. So for the other, you write this, and then you multiply, p, and then you subtract epsilon and p. But we know that the fatal, and of course the conclusion is that n G minus A Hamiltonian. If this holds, then that's Hamiltonian. If that holds, then that's fatal resilience. If we define it this way, then it's not true. So GMP is actually not fatal resilience. Not even for perfect matching. Instead, and what we think is the right notion is this shifted fatal resilience, which is you write the same thing, but here, or th, instead of p n minus I, you take a subtraction on this subscript. And I think, we think that this should be sufficient for Hamilton cycle. We didn't prove it, but at least this shifting is necessary to at least have a perfect matching. And we actually proved that this is sufficient for ensuring perfect matching. So if P is again C log n over n at least, and GMT satisfy shifted fatal resilience. With respect to perfect matching. So we couldn't prove the existence of Hamilton cycle, but with that condition, we can actually prove the existence of perfect matching. Okay. Let's see then why this is not enough. So you have a random graph, and you consider that there is some y and ny, and y, let's say, have size 1 over 2p. So you take a vertices, and then you consider all its neighbors. And this neighborhood is not big enough to cover all the vertices. So it's because every vertex here has we know that degree np overlap. And this has size 1 over 2p. And of course, we consider p satisfying those conditions. So this is not too small set, but anyway, its neighborhood is, not so big. you consider 100 say, epsilon n vertices, and 100 epsilon n minus say, I don't know, 2 vertices, and then let. And in here, we can actually show that every vertex has a correct degree to each of these sets, except y, because we already exposed the edges attached to y. So, for example, vertex here has a degree 0 to here, but within this, every vertex has a correct degree to other sets. We can actually show that. And we delete the all, so it's red edges are edges of H that we delete. We delete the order edges between X and left, except let's say this is U. These edges are surviving, but these we all delete. Then we can actually check that the 4 degrees of the vertices in X, it's a degree in H is 1 minus 100 epsilon and P. And for the vertices in U, its degree is 0. And remaining vertices, say not just U or Y. It's no edges are deleted here. And for the remaining vertices, B, it's more or less 100 epsilon and P plus small. Because this has 100 size 100 n. So typical vertex here or here has the number of neighbors to here is 100 epsilon n times P. So that's how many vertices they lose in the remaining one. And U or Y doesn't lose anything, X loses something. Something which is almost all except proportional to U. But it's easy to see that this doesn't contain any perfect matching because this has only neighbors here. But this is slightly smaller. And we can actually show that this satisfies the quartile resilience, not the shifted quartile, because from here, we know how many vertices are here. So if we write down the, degrees of H, it's 1 minus 100 epsilon n. Let me write it here. So 1 minus 100 epsilon n P, more or less this, or many times. How many? 100 epsilon n time. And then in the middle, you have 100 epsilon n P and 0. Here, this is 100 epsilon n minus 2 plus size of y. So you can actually check that this satisfies the quartile condition because of this y is at least 2. If y was not here, then this is, this is 2 smaller than this. So at these last 2 points, you are matched with these 2 numbers, which should break the quartile condition. So because of this y, it's extended a bit. That choice of y was taken so that there are additional vertices whose not losing any edges. So because of this y is at least 2, now quartile condition will satisfy. But this doesn't contain perfect match. In order to forbid that, now you add this. This is bigger than size of y. So with this, now we are forbidding this situation. Anyway, that was the reason why we have to consider the shifted quartile resilience. And in the remaining time, I will describe the, I'll give a proof sketch of this theorem of Pósa resilience. And
Do you think it's possible to extend it to the heating time bubble? Or you need like a really new
yeah, I think, I don't know, I mean, so the approach of ours would not extend it, but we have to take the approach of either Montgomery or Menado. And was anyway, that group. I mean, but I don't really remember how they proved it, so I don't know whether, I mean, that's possible. Anyway.
one more maybe naive or general question on heating time bubble. Because each time you add an edge to a graph, I guess its choice is kind of completely random. Like maybe like you can add edge, which is possibly quite far from the previous edge you added.
Yes.
Can you kind of restrict your choice to be maybe maybe can kind of enlarge your connected component? You can only allow edge whose one end belongs to something.
Okay, then it becomes connected quite fast, right? After n step, it's already connected. Every time the number of connected components goes by down by one.
Hamiltonian.
Yeah, once it's connected, then from that, I mean, so if there are only one component in your model, you add a edge at random, right? Then, I mean, it's I mean, once it's connected, now it I mean, to ensure Hamiltonicity, it becomes quite easy. I think after that, you just add like, I don't know, epsilon and more edges, then it might be already Hamiltonian. I'm not quite sure, but maybe probably that's related to the fragile paper of, I mean, Sangil and Lee and Mihyun and Dongyap. I think after adding like epsilon and more edges, it's already Hamiltonian.
So I want to kind of put the restriction from the beginning. Like
yes, from the beginning. So you after n step, it's already connected because of your restriction. Every time you add an edge between connected components, right?
You're saying that doesn't actually making the problem easier.
Yeah, much easier.
What was the assumption you were making?
Like you add one, and you can add only edge that's incident to the edge in the previous way.
So I'm gonna give a proof sketch of Pósa, but it will be not too different from the proof sketch of this circle because our proof, I mean, lots of main ideas are from them. So I want to mention that. Anyway, so let's say you have a G, which is G and P, and G prime, let's say this is minus H. And in this random graph, what we know is that we have, if you take any set x and y, then number of edges between them is more or less concentrated. So for any, so this is for all sets. If x and y are small, this error term is big, so it dominates. So for any xy, this holds. With high probability, this holds, so in G. So we can assume that this holds. And this x and y are allowed to overlap. But this edge, we count twice. Then you get, again, the same number. So that's one condition that we assume. And let's consider how we can prove Deryk theorem or Pósa theorem in the classical model. You consider a longest path. And then if you have two edges looking this way, then you take this cycle, and then because the condition makes you connected, so there must be this one, and you get a longer cycle. So this is called rotation extension technique. So that ensures that both edges cannot be there at the same time for the longest path. So that was the idea of Dirac theorem. And then you show that the minimum degree condition ensures that this actually happens. So how we want to do it, I'm not sure if I have enough time, but even if time is a bit over, then I don't think anyone will be that unhappy. Yeah, raise your hand if you are really unhappy. No one? I was actually wishing someone to raise your hand, and then I can end early. So you could take a longest path, starting from say B, and end at X. And what we do is we consider again rotation. So this cannot have vertices, neighbors outside. In that case, this wouldn't be a longest path. So its neighbor must be inside of here. So now you break this edge, then you can take this path, and this new vertex, there is a longest path between this and this now. So what we will do is, using that, let's say, it's R1, maybe B, so it's just X, let's say R0. Let's just say this is the end of this initial path, so this is the initial path. And then you do one rotation. And then this is now your end vertices. So let's say R1B is the all vertices, which is end of a path after and most say T rotation. So it has neighbors and say neighbors and neighbors, and this would be R1. And R2, from here, from each of the paths, you do the one more rotation, and you, get the end vertices, and that's R2. Then, what I want to claim is that, what we know is that this grows. So we can actually show that each time the set grows. Why this holds? One of the things is that once you take this, you have X, and you consider the next one and previous one. Once you rotate it, then you take the neighbor of the previous end. And now X plus becomes the, new end. But let's say you have Y plus, Y minus. This plus minus is, with respect to the original path. Now you add this. Then, now Y minus is added. Sometimes it's plus, sometimes it's minus. But if there is X and X minus, X plus, all of them are not in RT. And if X happens to be in the neighbor of RT, then one of these two surely will be in RT plus 1. But this X minus could be counted twice by the X minus minus here. So here, what's this? You subtract 3 times this number to only consider the X whose previous one and later ones are not touched. And then multiply, everything can be counted twice, so just divide by half. Because this is n because of this and because of this, they are counted twice, so we have to divide 2. So because of this, initially it grows. It grows to say some epsilon n size. You can actually show that this grows to certain size. So we can show that, let's say this is for some t, which is little over log n. After almost log n step, it becomes almost linear size. After that, I want to say that, by the way, all of these are done in G5, of course. After deleting that, we are doing this. And after that, we want to show that every time it still increases. Because, if this is large enough, then we cannot really say much about how large its neighborhood. So this wouldn't give you any increase at a certain moment. So we want to show that this holds. So you have this RBT, and then let's take A with the epsilon n vertices in this RTB with highest, not highest, lowest H degree. So H has degree sequence of this. To be precise, H has degree sequence slightly below because of that epsilon NP we take, subtract. And if you take this A, so this RTB is vertices with this many sides. So the worst case is that all of them are in here at this range. But even at that, you take the epsilon n, which is A, which has the lowest H degree. So you can actually ensure that these H degrees are not too big. That means if you count the number of edges between this A and the entire vertex set, it's at most, so there are A many vertices, and each of them has n minus, say, R T minus epsilon n. So this is exactly number here. But because of this shifting, so this yellow to blue, we have shifted a bit. So you can actually, show this. Okay. And now we have this collected one. And where should I? And now what we do is we consider this initial path. And let's say this is P1, P2, P3, Pk, where k is some large number times log n. So we break the passes into these pieces of the same length. And we consider x, which is in A, which is in RT, meaning that the Deryk is just a path from Bx has Px, let's write Px, is obtained after at most t rotation. So after t rotating, but t is little over log, so which is much smaller than t, k. After that, we get a path from B to X. And let's write, oh, it's already over time. Is there anyone who's really unhappy and stop this? Huh? Wait, was it 1 hour talk? Oh.
I mean, up to you.
So let's write this 3. So this is A, which has that Pi is unbroken in Px and traversed forward. And similarly, backward. And this Pi is broken. Meaning that if you have you did say rotation in here, then this is X, this is Pi. And to get the path from B to X, we broke this Pi. So that means X is in here, because Pi is broken. And so here, these are, if you start from here and come here, these are traversing forward. So, I mean, X is also in, X of, let's say, this is 3, then X of 3 plus. Because to get a Px, this is travel forward. And let's say this is Pk minus 1. And if you consider xk minus 1 negative, then it contains x, because in Px, you traverse this backward. Okay. So with that, we can actually show that we can ignore this. Ignore the third one. Just pretend that it doesn't exist. Of course, in the proof, you cannot say that. But the basic reason is that for each x, in order to get Px, you have to do the t rotation, right? So x belongs to t many of this. X, for each vertex x, it belongs to t many of this set. And t is much smaller than k. So let's write it this way: x and this is k, and you add an h if this a belongs to this. If this a belongs to x hat I, then you add an h. Otherwise not. And the degree here is at most t, which is real row of k. And here, backward, each of them has degree, small degree for most of them. So for most of them, this is small. And there could be few of them which may this be big, but we can later on the calculation we can just forget it. Then we can just ignore this. Now once we ignore that, let's consider this Pi. I have deleted one inequality that I was going to use. So we previously showed that, what was the number? So we had this, and then now what our aim is to lower bound this to get the information. That's what we want to do. So for that, we forget the x hat. And then now you consider the pi, and you forget the boundary. Boundary is just the k-many boundary point, which is log n, which is again small, so we just forget. We are not sure what we are forgetting and for what purpose, but let's just forget. And let's consider the number of edges between this xi plus and this p, or precisely interior point of p, minus, RT minus. So RT minus is RT plus 1. So RT plus 1 is the next, one that we want to measure. But here, if you have this x, so this x is in RT. And if you add this, this is traversed forward. That means this is in RT plus 1. So if you shift it by 1 to the negative side, and then you delete it. So in here, you delete it for every one of them. Then between these two, there should be no edge. G prime. So which means every edge here also must be in H. And this is set of, this is set of size n over log n, roughly n over log n. This is also set which is considerably big. Small set we can just forget that, because we divide the entire set A, which is epsilon n size, and you divide into k-many. So each of them are roughly, you can consider n over log n. So between these two, in G, we already know how many edges are there. And they all go to H. So this holds for most of the I. And for negative, you can again consider this with a plus sign. So these, out of these sets, you know that you know how many edges between this and certain set, and this and certain set, this and certain set. And these sets are exactly the, on this path, you just forget the boundary. And you have this set A, which is partitioned by xi plus xi minus. And then each of these terms measures the edges here, edges here, edges here, edges here, edges here, edges here, edges here. And out of P, there are some vertices, but there is no edges between this. Because otherwise, if there is an edge, you can extend the path. So that means all of these edges are already deleted. So they all belong to H. These all belong to H. These all belong to H. So you just add up. While adding up, you have to compute the error term, which I said that we can forget that. That all contribute to the error term. Then you can do the computation that this is at least A times D minus RT plus 1. So this is N minus RT plus 1 times P minus little o and scale P. So you just forget everything else, then you just move this and move this, then you show that the RT plus 1 is RT plus epsilon n. I mean, the error term maybe make it to epsilon n over 2, but so it increased. So Ri keep increase. That's what we just showed. And what do we know? It cannot increase, I mean, arbitrarily. It can increase up to size of half plus epsilon n. You cannot get bigger than that because of our condition in the Pósa condition. It starts to stabilize at a certain point. Then what it means is that for each B, you can find the set RB. So that between B and RB, there should be no H. So RB is size half plus epsilon n, which you get after doing this a lot, and you get the size, I mean, this much. So between this B and here, if there is an H between B and RB, then what it means is that you can find the path, longest path from B to some X in RB. And then if there is an H, then you get a cycle, and then which will be extended to get a longer cycle. So there is no H between B and RB. And for each of these vertices in RB, you can consider another path which starts from X and ends at B. Well, same path, but before you grab this and then you take the rotation. So now you take this and take the rotation. And what you get is that for at least half plus epsilon times n vertices B, there is RB such that it has set this many sides, so that if you have a H between them, then you get a longer path. I mean, if this B and RB is pre-chosen, then this would end the proof, because I mean it's too unlikely that you have one vertex enlarged that there is no H, right? If this was independent of the random graph. But sadly, these actually come from the random graph, so there are some dependencies. So, I mean, for all we know, we have this neighbor, and then this RB must be conveniently out of neighbor for all vertices. That could happen, right? So we cannot directly say that this would end the proof, but we can actually, I mean, yeah, do some tricks of like you first show that if you have some G0, let's consider some graph G0. Which is good. GNP, good, and number of edges is smaller than some number. GNP has edges between B and RB. Give me 3 more minutes. I will. Yeah. So which actually comes from this G0. So G0 good means that we can do the all previous thing. It doesn't have to be a random graph. Any graph, we can do the previous thing and then get B and B0, B and RB. And we consider all those graphs. And then show that with high probability, this GMP satisfies that for all those choices at the same time universally. So GMP with high probability, I mean, for any choice G0, we can, I mean, for any choice G0, we can find the H, which is in GNP. GMP H between those two. So we show this, and then we show that this GNP minus H contains at least one, sorry, not GMP, GMP minus H. So, yeah, at least one G1, which depends on H here, such that it is good, and number of H's is almost this. So we first prove that this can, deal with all those choices, which doesn't have to be random. And then we show that this, for whatever H we take, we can always find one in here, which satisfies all the good properties here. So whenever H is given, we find, one is graph. But we already have shown that all those graphs are, taken care of. So this is just one of these G0. So with this trick, we can show that, every time you take longest path, we can actually extend it. And, which shows that we can actually find the Hamilton cycle. So, most of the main ideas are from Lee and Sudakov. Except we change it to the Pósa setting, and then, yeah, some of the details and some twists that we introduced. Anyway, yeah, so it's well over time. So I will finish the talk here. Thank you.
Any questions?
Question. In the counter example you had to the non-modified version, you had the -2 in that set. Can you write the -c for any c? Or is it just?
Yeah.
So it's even an approximate version of a perfect matching you can't find without the modification.
Right. Okay. Yeah. Constant. No problem. And yeah, I don't remember exactly. You can maybe do the calculations of. Anyway, constant is fine.
Is there some universal tool that, given some property with a certain actions, can you so that you can use that tool to prove that something is resilient? Like if I know some result like about random graphs with certain probability, and this method is very specific to the Hamiltonian cycle. Right?
Yeah.
Is there some more general method where, give a certain property, we can say many of these properties all are resilient?
I'm not sure. But some of the previous results. For example, the Hwang and Lee Sudakov, and independently by Allen, Bocher, Aaron Mueller, and Taras proved the resilience for bounded degree graph. So there, what they did is kind of prove the resilience version of bandwidth theorem. So bandwidth theorem, you have a complete graph, and then your minimum degree is at least 1 minus 1 over R or something. Then you can find the R chromatic bounded degree graph, which is separable. So there, I don't exactly know how they proved it, but the original bandwidth theorem is proved by using regularity and then blow up. So maybe they use the sparse blow up lemma. So sparse blow up lemma is a kind of universal tool you can also find. So sparse regularity lemma, you take a random graph, and then you take the subgraph. There, you embed some structure that you want. So maybe that's something that's close to what you mentioned.
And I can I have is that there are many properties that people study for GMP,
Yeah.
like whether or not you have a giant components or
Yeah.
whether or not truth is unbounded or bounded. Do people study the resilience version of these well-known facts? Or
I don't know. And one thing I forgot to mention is that people also do consider about random regular graph. So if you consider random D-regular graph, so it's known that it's recently Condon, Diaz, and Jirao, Kühn, Osthus. So same as previous, but I was kicked out and then Jirao was put. They proved that this is also resilience, with respect to Hamilton cycle. So they have proved it, the random regular graph for all d larger than certain absolute constant. So before it was known for d at least say super logarithm, log n plus 1 plus epsilon, it was known because above that the graph is expander. So you can consider the eigenvalue, and its second eigenvalue is sufficiently smaller than the first eigenvalue. And then there is some result proved by Sudakov and Krivelevich, and yeah, I don't remember exactly who, but proved that if you have an expander graph, then it's resilient. So above this is the expander, so it is known. So that the unknown case was that the constant between this and this was unknown, but recently, Condon, Diaz, Jirao, Kühn, Osthus, proved that this is also resilient with this degree. Hamilton cycle.
right, any other questions? Maybe we should finish and then continue discussions.
1 hour and 15 minutes.
Okay,
What was the record of the longest talk?
okay, let's thank the speaker first.